learn some stuff?
Learn some stuff maybe.
It's not warm enough.
Also no tiny top.
I mean, do you guys have, is there like a mobile chalkboard we could use? In a mobile whiteboard? We could do that one day. That's really nice.
It's gonna be like 70 degrees Wednesday.
If we have a mobile chalkboard, is there like a patio or anything we can go out around here?
Yeah.
There's the one in front of the other door, but that'd be a little weird.
So we want to use Lagrange today, and apparently I need to do harder stuff because you guys are going to Mary Beth's lecture.
Not everyone.
So you want to see harder examples?
Not everyone.
We just want to see more examples.
Yeah.
More examples, okay. Well, I mean, that's fine. You guys can
Can we,
always
like,
stop me.
Can we work through an entire example with like the Lagrange thing, just like beginning to end?
Yes.
All the gross,
We-
disgusting.
Definitely do one of those. I was looking at some. So we didn't finish a problem on Friday. Let's do. That's what max min over R divided by some function. Let's do this. So the notes. We want to find the absolute max min of a function f of x y is equal to xy on the region R given by x squared plus y squared is less than or equal to 4. So the old way we have to do it, we actually didn't work through how to do it, and we should work through how to do both examples, both using Lagrange multipliers and with just parameterizing the curve, parameterizing the boundary. Sometimes one way is easier than the other, and you kind of got to recognize whichever way you want to try on the exam. Hopefully you kind of guess the right way the first time, or guess the easier way the first time. So our steps with this were to compute our gradient, set it equal to 0, so both our x and y are going to be 0 here, and then we compute our second partials. It's fxy. One. And so the Hessian is negative. So we know that we're going to have a saddle. What does this tell us? So we are satisfying our extreme values here. We have a closed boundary region, functions, continuous, differentiable of all orders. So we should have a max min somewhere. How do we find them? Well, it's not on the interior. That's what we know. It's not at the origin. There's nowhere else it could be based on our first derivative, based on our gradient. So we have to check the boundary. The boundary is going to be where we're equal to the circle. And so our first method is to parameterize. Calculate this thing. So what is our parameterization of the boundary? Do 2 cosine, 2 sine. Meaning that on the boundary, our function f of xy is going to be 4 sine t cosine t. guess you could use count3 if you want to use the chain rule. Now that you have x and y dependent on t, do your gradient and then dot product with r prime if you wanted to. Or, again, like a lot of times when we're just substituting in, usually the functions are easy enough. It's almost easier to do this, and then, sorry, this would be f of t or f of r of t. Now it's a function of time, so we can just take a time derivative. So, t dt this guy. And we'll get 4 sine t squared plus 4 cosine t squared. Yeah? Did I do this right? Yes. Want to check where that's equal to 0. And what are we going to have? We're going to have sine squared t equals cosine squared t, or tangent squared t 1, tangent t is plus or minus 1. So what are our t values? Pi over 4. So t is 4, 3 pi over 4, 5 pi over 4, and 7. Once we have those, we would actually want to check our points. So we know we're at x squared plus y squared equals 4. We would want to check those points and plug them into the function. So however you want to do it, let's actually plug in the points, I think would be a good idea, just because we do want the x and y values. So this is going to correspond to our x, y of pi over 4, so we'll have 2 over 1, 2 over root 2, 2 over root 2, and then pluses and minuses of that, so 2 over root 2, x is negative, some is positive, both are negative. And then both are first one. Or
Second one's negative.
second. Thank you. Those are our 4 points. Question?
Oh, I was gonna say.
Yeah. And then, of course, we still have the saddle point. I guess the fact that we know it's a saddle tells us that it's going to be going up and down on either side. Of course, if we plug in the value of the saddle, that's going to be 0. And so where are our max mins? So max what's the max going to be?
2.
2. Yep.
And then minus 2.
So we're plugging in these points into our function x, y, so just multiply your x's and y's. The maxes are going to be where it's positive. So it's going to be over where both are positive or both are negative. Min minus 2 at the other points. So that's our process. That's how we check our boundary. Once we have a parameterization, it's a calc one.
So there was this question similar to that on the web sign that's due, like the upcoming web sign, that was basically exactly the same as this, just with a different formula, and I didn't yet know how to do this, so I just guessed and checked the point if I were to take the gradient at the only critical point on that function and extend it, and that was the maximum, if there's only one critical point, is that valid? Just
Say
take,
that again?
if there's only one critical point on a function and you're asked to find and that's a saddle point, and you're asked to find the absolute max or min on a circle, can you just take like the gradient at that point and extend it? Or
Gradient at that
or not the
point is
gradient.
zero.
Yeah.
I don't know.
The
I
gradient
don't know
at that
exactly
point is
how I
zero.
figured it out. No, it was, the slope was, okay, never mind, answer my question. I know, that's what I was gonna do.
This is the best question. Okay, so our other method's gonna be Lagrange multipliers. So let's talk about those real quick. They actually come in handy. I think when capable, I prefer to use Lagrange multipliers. So let's talk about sort of in general what's going on. Our theory first. And we can use this function at least as an example. Let's take a look at the level curve. So this function x times y is a saddle. It's a hyperboloid or whatever the name is. So it looks like this, or at least our level curves are going to look like this. Where on one side it's going up, the other side it's going down. Let's see, we found our maximums were here, right? So I think these ones should be going upward. So our gradient on these guys is going to be pointing this way, whereas the gradient here is going to be pointing, oh, sorry, other way. Yeah, that's decreasing. No, never mind, I was right the first time. So we should be increasing away, and then we are decreasing on these ones. So pick whatever the values we have. So this is, so 0 is going to be our x-y axis. This level curve might be something like 1, 2, 3, 4, and then these ones are going negative, negative 1, negative 2, negative 3. So what do we want to do? We want to find the maximum of this function, but we are on a circle. And so our idea is that instead of parametrizing, or at least we can use this notion of parametrizing, to see what's going to happen if I'm walking around this circle. All right, we want to walk around this circle, and if we go this way, we'll be going up. We can kind of see that we'll hit a max here, then we're dropping down, and then here we're going lower. So we want to know just in general, if I have a function we are trying to optimize over a given region, where do we need to walk in this region so that we hit the maximum values of our function? And we want to use this notion of our level curves and our gradients. So our idea is that, well, if we know at every given point, since the function is defined all over this domain, we can think about which direction the gradient is pointing. So let's say we're here. Our gradient is always going to point towards the next level curve, right? It's always going to point orthogonal from our one curve into the other curve. So no matter where we're at, the gradient is going to point in a direction of greatest increase. Yeah? So this kind of tells us, well, now if we look at our component vectors, if I'm walking around this circle, I'm always tangent to this circle, or at least our directional path. So what's it mean, like, so let's say we're at this point. If our gradient is pointing in this direction, and my tangent vector to the circle walked points in that direction, should we keep walking if we want to increase? Why is that? How do we know?
There's a third vector, isn't there, that tells you walk in this direction a little bit.
Projection.
Yeah.
The projection
projections. Yes, exactly. Namely, if our velocity has a non-zero component, I guess we should say the other way around. If our gradient has a non-zero component in the direction of v, then we should keep walking. Then, if we move in the direction of v, f will increase or decrease depending on the magnitude of that component. So if our component is negative, if our goal is to increase, is to find the maximum, of course, as soon as I have a negative component in that direction, we would want to walk in the other way. So we keep walking, and what's going to happen, we found our max here. How can we tell we have a max now in this type of analysis? We have a direction we're walking, and we want to compare it to our gradient. What's going to happen?
Your,
When it goes from positive to negative.
Yeah.
yeah.
And if it has to go from positive to negative, it has to be zero. Yeah, at a specific point. So at max mins, the gradient of f is orthogonal to v. Okay, but we're still on this parametrization method. Parametrization helps us. Let's suppose before we have a parametrization, assuming that maybe a parametrization of our boundary exists, but if our boundary is given by some level curve, then what's another way we can rephrase this condition? Our gradient of f has to be orthogonal to the direction of v.
Direction of the gradient is the scalar multiple of the direction of v.
Exactly. Then our equivalent condition says that the gradient of f has to point in the same direction as the gradient of g, because we know that the gradient of g is going to be orthogonal to our directional vectors of the level curves of g. So the gradient of f has to be a scalar multiple of the gradient of g. And so that lambda is our new variable we're introducing as this multiple. So let's see. So let me erase all this.
That totally looks like a person holding a shield cutting off like the dragon. It's like G is the dragon. Like, okay.
And
Can I get clarification on defining G here and like how we go from our boundary equation to like this G that we can take a gradient of? Right? Yeah, because that's a 2D function, right? And
Yeah.
so we are assigning.
equal to a constant. So our boundary is defined as a level curve.
Okay.
So we can parameterize the boundary, but there are often times when we can't come up with a nice parameterization. Right? The function could be x squared minus x square root x minus y equals 3. Right? parameterization might be kind of hard for this, because it'd be hard to solve for either x or y. Might be able to solve for y. But now at least we can define it as a level curve and now use these gradient values. So what we can do is introduce this notion of the Lagrangian. This will be slightly different than the way the book does it. We can introduce a new function of L, x, y, z, if there's a z. In this case, it's just going to be x, y, lambda, which is equal to f of x, y minus lambda times g. So this Lagrangian is a new function we're introducing that encodes both the value of the function we actually care about and the constraints. It's kind of just a fancy construction at this point. Though, some of you guys, especially if you get into like advanced mechanics, advanced physics, you'll see Lagrangian functions everywhere. Once you kind of get up upper division undergrad, maybe graduate level, entry graduate level classes, when you look at a lot of like mathematical methods in physics, a lot of these problems are all about optimizing your Lagrangian. In other words, finding the max mins of these Lagrangian functions that are defined differently in different situations. So this is kind of like an introduction to that. Why do we like this function? Well, it encodes f, it encodes our g, and if we were trying to optimize this function now, what do we mean by optimization? We take the gradient and set it equal to 0. So what is our gradient of our Lagrangian? Well, we've introduced an extra coordinate, an extra variable, this lambda. So what are we going to have? We're going to have, let's write it out as Lx, Ly, and now we have an extra partial derivative to take, L lambda. You could have 4 if these are x, y, and z functions. Could have even 5 if we have 2 constraints. So what are we going to get? Well, what is Lx? That's just going to give us fx. Fx minus lambda times g of x. Ly is going to be fy minus lambda times g of y, g sub y. And what is our L lambda going to be?
Minus g.
Minus g. And so when we want to optimize this, we want to set this equal to 0. So finding critical points of our Lagrangian is going to be equivalent to what we want. And why is that? Well, this just tells us fx is a scalar multiple of gn. It tells us that fy is a scalar multiple of gy. And then we also have this condition now that g of xy is 0. This condition is the same as this condition over here.
Which kind of makes sense because those are both vectors and you just distribute the constant, kind of.
Yep. Yeah. So Lagrange multipliers, however you want to frame it, if you want to use this method or if you just want to use this standard method, we have, was it like n plus 1 constraints? So if n is the dimension, we should always have n plus 1 constraints. Namely, the gradient is going to give us n constraints. So if we're in 2 dimensions, here we're going to have 2 constraints. Namely, fx equals lambda lambda gx, fy equals lambda gy. And then our extra constraint is the constraint function, g of x equals 0, g of x, y. Yeah.
G of x, y equals 0 is not G of x, y equals 4. Those are different things, so you're constrained.
Those are totally different things. Did we make a mistake? Good enough. We've got a new g.
Okay, so when we define G to do this thing, we
Yeah.
need to write it like that.
You should set it equal to 0. Yeah.
Okay, see, that's, okay.
Yes.
Important, because if I take that and I try to throw that into G, then when I do this stuff, it's gonna
Yeah.
mess
Yeah.
things up.
That is, you would be off by a little bit, right? Whereas here, of course, if we're keeping track of our gradient constraints individually and then back to the original constraint, Same thing. Yes, just be consistent on your constant. Okay, so if we want to use Lagrange multipliers on this, we can have our g. So we can say x squared plus y squared minus 4. We call that our g. And then, however you want to organize your work, Lagrange is xy minus lambda times x squared plus y squared minus 4. Take a gradient of this guy and set it equal to 0. So let's get some more board space. Yeah, so this is actually a thing that actually comes up in optimization a lot. I was just catching up on machine learning and optimization. And a lot of the ways we phrase optimization problems, we almost always phrase our constraint problems as comparing it to 0. Mainly because we can always just shift around the constants. But it is a thing. It is a thing to keep track of. So what is our gradient of L? Is going to be our fx, which is going to be y minus 2 limit x. Our fy is going to be x minus 2 limit y. And then our L sub lambda is going to be this. And when we set each one equal to 0, all of that information. Of course, another way we could write it, or when we go about solving this is gradient of f, or at least our partial derivative of f, equals our partial derivative of g with respect to x. All right, so let's go ahead and start with this one since we already got it going. And let's plug that into our second equation. The main tricks or the main algebra of work in this problem comes down to, well, 1, computing your derivatives, and then 2, solving a system of equations. So a lot of substitutions going on. We will have x minus 2 times lambda, and y is 2 lambda x. What does that give us? X minus 4 lambda squared x. So either x is 0, we get 1 minus 4 lambda squared is equal to 0. And then, so what, our lambda plus or minus 1/2.
Oh, okay, I see it. I see it, I'm sorry.
Yeah, your lambda has been changing
Yeah.
over the course of this lecture.
Lambda should be more like this, but when I write fast, it ends up being not that.
I mean, it kind of simultaneously looks like a y and also a lambda and an x, 'cause it's just like
Lines.
lines, so many lines.
I think our problems ask you to use you and me, and when you have bad handwriting, they look not having a house.
Yeah. So how do we want to go about solving it? A lot of these problems, there is kind of one general technique. Oftentimes you will solve x and y in terms of lambda, then plug it into your constraint equation, find your lambda, and plug everything else back in. Doesn't always work out that way. Sometimes there's different ways of solving it. Of course, if x is 0, we would solve for y is equal to 0 as well. That would actually find us that saddle point. Of course, we wouldn't satisfy this as x and y both 0. If our lambda is plus or minus 1/2, we can't plug it back into this equation, but we can plug it in here. So this would tell us y is equal to plus or minus x. So So if y is plus or minus x, now we can plug it back into our constraint equation. We can call this 1 prime. And so we get x squared plus minus x squared minus 4 equals 0. So 2x squared equals 4. And so we find the points that we found. Careful with the plus or minuses. Sometimes you can take those independently, so you have different choices. I'm going through this a little quick.
Wouldn't it just be root 2? Or 2 root 2?
Yeah.
Not one
It's
over root 2.
x squared is 1/2, or x squared is 2. Plus or minus root. So we found it last one. I thought we found. Oh yeah, we had 2 over root
2 over root
That's why I
2.
was confusing myself, which is root 2. Yeah. Right. So careful with the plus or minuses. Here it doesn't matter because we'll square it. But here, as you have plus or minuses, sometimes you have to just choose those independently. So right, if x is plus, y is going to be plus or minus that. So our points, when we choose positive for x, well, if x is positive root 2, y can be plus or minus that. So there's extra combinations. Just make sure you don't miss them.
Just take all the points. Just go along the boundary to everything.
To every single one. Yes. And then of course when x is negative, same thing. Y can be plus or minus based on that negative. And that's it. So that's Lagrange multipliers. We found same points, same methods.
And you plug that back into the original equation, right?
Yep.
Find maxes and mins.
Yeah, plug them back in to find maxes and mins.
Does the value of lambda itself have any significance at all, or is it just sits there?
Kind of just sits there. It really doesn't have that much significance, at least not that I can think of. I think in other contexts it might, but for this problem, not really. Not for count 3 problems. Because it is just that scalar multiple, and it can change. Like you could model your problem slightly differently for the same problem and get a different lambda, but the points are still the same. All right, so that is it. You guys are done with differential calculus.
Yeah.
This is the last topic in our derivatives. What do you guys want to see now? More examples?
Sure.
That's all that's kind of on the notes for Lagrange multipliers. Just more examples now. Unless you want to see one with 2 constraints. Pull one out of the book. So on 2 constraints, like if we have something like g of xy z equals 0 and another constraint, so let's suppose we have f of x, y, z, and we want to optimize subject to our constraints. The same kind of diagram applies. You might just have to draw like different level surfaces and level curves, but really all it's going to say is that the gradient of f isn't necessarily going to point in the direction of g, because it also has to point in the direction of f. So it doesn't point in either direction, it points in some optimal combination of those two, where we remain on the surface of intersection. So it has to be lambda times the gradient of g plus, usually we use mu times the gradient of h.
What?
It's log plus m.
Yeah. Plus
Well said.
It's kind of like, so if we have our level curves, but then we have, it's hard to do in 2 dimensions. We we have some G, so this is our G, and our H. Well, unfortunately, G and H, they only intersect at 2 points. So those ones you check by hand, but let's say they intersect at a bunch. We want to know like which one's going to be optimal. You kind of have to think, well, the gradient of F is pointing in a certain direction. And so that in order to find the maximum one and stay on there, it's not necessarily going to point in the direction of G or in the direction of H, but in a combination of the two. This is a vector, this is a vector, and we're just taking different scalars and adding. We will not ask a question like this in this class. Don't worry about it.
Okay, so what are G and H? Are you saying that it has to exist on those curves or within?
These are our constraint functions, right?
Yes,
we
are
have
they
to-
within or on?
We have to be on both of these, but sometimes they could be, I mean, they could be higher dimensions, right? If G of X, Y, and Z is equal to 0, you know, we could be on
Yeah.
some sort of this, and then we could have H as maybe a cone. And so we have to be on the intersection of these two, which is gonna be some wonky curve. And then we are optimizing this function.
Would that function be like a 4-dimensional thing then?
Yes, because it would be f of x, y, and z. We would need 4 dimensions to model it.
When would you ever need to do that? Aside
Well,
from
you guys are gonna be engineers.
More
you
dimensions.
Probably.
You're in CS.
I know,
You
I
can
was
be
gonna
working with
say-
n dimensions.
Okay, but n dimensions is just like, oh yeah, whatever, you don't really need to visualize it, because it's just a bunch of data.
Well, yeah, but you'll still have to do the math, whether or not you can draw it.
So the other example in the notes, we have some temperature in space is equal to 400 y z squared. We want to find the max temperature subject to our constraint where we are restricted to the sphere. Sphere of radius 1, so the unit sphere. Of radius. So what do you guys want to do? Lagrange multipliers or parameterizations?
For a sphere?
Probably Lagrange,
Yeah,
because
let's
that's
do
what we just
Lagrange.
talked about.
This was the trick question because we haven't learned how to parameterize surfaces, which I need to show you guys how to do. I'll have to do that in a project or something. I think you guys should do it. You're getting happy about it, right? And parameterizing a sphere is pretty easy once we get into spherical coordinates, so we can talk about it then as well. Once we get into coordinate transformations and integrals, maybe we'll talk about that. But yes.
Do you need 2 parameters for a surface?
Yeah, so how do you, we talked about this when we parameterized a plane, right? If my plane has directional vectors u and v, normally we cross product them to find our normal vector, right? But we could just parameterize it using 2 parameters. Sorry, let's not use s and t. Is whatever point we have on the plane plus t times v plus s, or let's do s times v plus t times v. My letters are all backwards. Not in lexicographic order. Right, this is saying I can start at r naught and then walk as many units as I want in the direction of v, walk as many units as we want in the direction of v. So this would be an example of a parameterization of a surface. We need 2 independent variables. So if we were to try to parameterize our sphere, we need 2 independent variables, which we don't really know how to do yet generally, and it takes some practice. So since we can't parameterize things, or at least don't want to parameterize things, Lagrange multipliers is basically our only method. So let's do this the other way, so our standard book way. So we have our t. What is our g of x, y, and z?
4
what's our temperature?
Not this, the sphere.
Yeah. Our constraint
Oh.
function is where we are glued to. We're glued to the sphere radius one.
X squared plus y squared plus z squared is 1. Minus 1.
Yeah, -1 is 0, because
Yeah,
otherwise we're gonna
because-
fuck ourselves over.
So you can say -1 equals 0. If you do it kind of the standard book ways, we kind of don't have to subtract that. We can just keep track of this equation and then compute our pieces. So our gradient of t is going to be 400 z squared, 400 xz squared,
800 xy.
800. Our gradient of g. Nicely enough, no matter where you put the constant, not going to affect the gradient. And our optimization constraint is that these two should be scalar multiples of each other. So we just now get our system of equations, 400 z squared equals 2x. This one might be a pain, if we use this for it.
Where's your lambda?
Lambda times 2x, yeah.
And then we just put it into the social media.
Lambda x. Be one equation. We've got 400 z squared equals 2 lambda y. And then we have 800 xy equals 2 lambda z. And then we have g.
That's a lot.
So, how do you guys want to go about solving it?
Solve for x, stick it in there. Solve for z and stick it in there or something.
Use the one that doesn't have squareds first.
Okay.
That one doesn't have anything squared, use it first.
Then what do you want to do?
Throw it around
I'm gonna
until
leave
it all
this
makes
to you guys.
sense.
I don't want to do it. This is
Solve the.
You
Throw
guys-
it around until
we're
it
gonna-
makes sense.
I'm gonna make you guys do all the grunt work. Grunt work.
Ask this symbol out.
400 x, y over z is lambda.
Well, is better.
So we can
Yeah.
solve each of these for lambda and set things equal to each other. That's another technique that's commonly used.
Oh.
Maybe we'll try that method. Let's solve each one for lambda.
So then you can get rid of the 400s.
Yeah, that's kind of why I want to try to do this. So other techniques, sometimes we can solve for lambda and get rid of all the lambdas. We divide by 2, that'll give us 200, and then yz squared over x. This one will say lambda, that'll give us 200, is xz squared equals y. And this one says lambda is x, y, over z. Plus some constants. Did I just forget all the constants?
Yeah. Which I
Uh,
mean, lambda is arbitrary, right? So we can just say it's like 2.
You could.
You could just say it's 2 x, y, z, and
You could multiply all your lambdas by 100 or a factor of 100.
Wait, what constants? Oh.
200, and then we had a 200 here. Yeah, you could say lambda 2 is 200 times lambda 1, and then get rid of all those. Okay, now how should we solve?
Set them equal to each other, get rid of the 200s.
Yep, so pairwise set them equal to each other.
oh, pairwise.
1, 2, and 3. Let's do 1 equals 2. What equation does that give us? So the 200s will drop then, and then we have yz squared over x is equal to xz non-zero. We can solve that guy. Let's go ahead and do some of that one. So 1 equals 3 gives us y z squared over x is equal to 2xy over z. It may not be easiest to start with that guy since it's the odd one out in terms of the power. So, what do we get here? Two solutions. First solution is z equals 0. Or, if z is non-zero, we get y over x equals x over y. I'll go with 1. Both. xy,
Y squared equals x squared.
which reduces to
Y equals plus minus x is minus x.
yeah. So same absolute value. Y equals plus or minus x. So if z is equal to 0, can we solve anything? Not here. Z can't be 0. Z can't be 0. Maybe our original equation. So before we did division, if our z was 0, x is 0. Here, if our z is 0, y is 0. So if z is 0, it forces everything to be 0. So in this case, we get a degenerate point. However, what happens if we try to plug this one in?
It doesn't fit on our sphere.
It doesn't fit. So this would be probably a max min. Of course, if we just took the gradient of t, we would probably find 0, 0, 0, but we're not on this sphere. So this one's not going to work. So let's stick with this, y is plus or minus x. And so what are we going to get? Plus or minus x, z squared over equals plus or minus 2x squared over z. So the x's will divide, and we get plus or minus z cubed equals 2x squared
Plus or minus 2x squared.
plus or minus 2x squared. And so to check those pluses and minuses, I think they will divide, because if y is minus x, we'll have a negative here and a negative here. Those negatives will cancel, right? Same thing with the pluses. So those aren't independent pluses or minuses. We can actually get rid of them.
Okay, but one of them's squared, so that one will always be positive, and the other one's cubed.
No, not necessarily, because when you plug in the y could be a plus or minus x. So if it's a minus x, you just stick the minus out front before you multiply the two x's together and make it squared. So it is technically, because like let's say x is positive 2, y is negative 2, then it's negative 4 even though it's 2 squared. That was a really bad explanation, I'm sorry.
Are you saying, yeah, because we get the negative sign here? So if y is negative 2, we'll have a
No,
negative here.
when you substitute in, you got 2xy, you substitute in x for y on the right hand side.
Oh, so
It's
this
still
one's
plus or minus, even
Yeah.
though that's technically x squared.
Right.
Because not
if
both
the-
I
of the
just
x's
mean
are
this thing over here, the z
Telling us
cubed.
that z has to be positive.
Yeah. And that doesn't cause problems.
We'll see when you check it. I don't know. I mean,
I'm pretty sure.
Does it cause problems with
basically from
wiring
what this
to be
gets,
positive?
like, kind of like Joanne was saying, that plus or minus factored out. So if y was negative, the negatives would cancel. And so we are kind of essentially showing that z has to be positive.
Okay.
If z were negative, then that term would be negative. That term would be positive.
Okay.
Okay, so that is not great. What do we have? Y is equal to x. We have z is something of x. So z is cube root of 2, x to the 2/3. So we have x, y, and z all in terms of x. Now what do we want to do?
Solve for
Because it
x
was
instead of
Friday.
equal. Solve for x instead of equal.
Well, no, how do we solve for x?
Could you say z cubed over 2 is equal to x squared, and then y squared is equal to z cubed over 2, would that help at all?
Should. What equation haven't we used yet?
Oh.
Yeah, so, right, in the last problem, we solved everything, lambda is equal to this, or no, we solved x is equal to some function of lambda, y is equal to something of lambda, z is equal, then you plug all of those into here. As soon as you have all the variables in terms of one variable, you can plug it back into your original equation. So let me erase this part here. So x is x, of course. We know that y is plus or minus x, or if we go back one step, y squared is x squared. And unfortunately, we got z cubed. That's annoying. We could solve everything in terms of z. That'll help. Let's do that. I mean, it'll probably be messy in the end. So x squared is z cubed over 2. Y squared is x squared, which is z cubed over 2 again. And then z is z.
What were you plugging in? Oh, into g.
So z cubed plus z squared equals 1. Is our solution. So whatever, solve for that guy. Which we can't do. Unless you know the cubic formula.
No.
There is one.
There
song
is one, but it's nasty and I don't wanna.
There's no song for it, so.
There's definitely not a
There's a
song.
song for the cubic function?
No,
For the
quadratic.
quadratic.
Or for the quadratic, there's a
X
song.
equals negative b.
Let's see,
plus
did we
minus
make any
x
mistakes somewhere?
x squared plus 4ac. Oh, well, do it.
Where's this?
I never learned it either, don't worry.
I did not know that was.
I just memorized it.
I memorize it first, if I memorize the song, that's what I'm very, very happy.
So we got 200, I erased all of it. 200 x y over y.
It's like,
X
you know when
equals
people
to-
say
say
acronyms
all
for
those
certain
equal to
things,
each
like
other. Yeah. Z
big
is-
elephants don't always whatever.
Uh-huh.
Somehow those things make me remember whatever it is that can help me remember less. And if I had
Did we
not
do one of these
before,
wrong?
who knows if it's right.
So the solutions on the notes have something slightly different. They just use these equations. Solve for lambda, they have, we said this guy equal to that guy. Probably not in there. Let's see here. We have time.
Yeah.
You have to check the gradient of t.
Yeah. So check your solution. I'll leave it to you guys. Start with the original equations. We had it right. It just kind of like comes down to like which variables you want to solve for. So the notes did this one, and then I think instead of doing 1 equals 3, they might have done 2 equals 3. So check if we take this equation and that equation. So this guy
Did we
equals
not use
this
two?
guy. We used 1 equals 3,
But we never used 2 equals 3.
but we never used 2 equals 3.
Yeah, okay.
It should, I mean, it all should still be logically equivalent, but we might have made an algebra mistake somewhere if we're not getting the same solution. So if you check the same way, when we do 1 equals 2, that was easy, x equals y, but if we do 2 equals 3, it looks like you get like z is equal to y squared or something like that. So if we take this guy instead of equal to this guy,
I'm
X's
just
will
confused that
drop.
we didn't need to use all 3.
nah, because they're equivalent. As soon as you have like 1, 2, and 3 all equal to lambda, this is why we have symmetric equations for lines. You actually only need 2 pairs of equations. And then the third one is logically equivalent, so it's,
I see.
yeah. Anyway, check. And then I guess on Wednesday, are we starting integrals? What's on the schedule?